All right, welcome to section 5.1 and 5.2. All right, so this section we're going to talk about exponential functions. All right, so an exponential function, if b is a positive real number and b is not equal to 1, then the function f of x equals b to the x power is an exponential function. The key here when they say exponential function is that the variable is in the exponent. Okay, so that's the key. Exponential function, the variable is in the exponent. So the constant b is called the base of the function, and the variable x is called the exponent, like I just said, right? So graphs of exponential functions, you don't have to memorize this, just be familiar with it, especially if you're moving on to pre-calculus or calculus after this. So it does not, the graph of exponential does not intercept the x-axis, right? So the x-axis is an asymptote, right? So it's going to get closer and closer, but it's never going to reach that x-axis. Y-intercept 0, 1. Domain is all real numbers. Remember, domain means all the possible x values, right? The inputs. The range, anything greater than 0, y greater than 0. Again, it does not go below the x-axis, so remember the range is the y values. Like I said before, the horizontal asymptote is the x-axis. All right, and you can see the two shapes, right? So if we have a negative x power, it goes off to the left here, or it goes up to the left, and if it's a positive x exponent, then it goes up to the right. All right, so last chapter we talked about shifting graphs, right? So you should be able to just look at a graph, or I'm sorry, look at a function and see where it's shifted, left, right, up, down, stretch, compress, etc. All right, so explain how the graph of each of the following function compares to the graph y equals 2 to the x power. So notice 2 to the x power. The difference here, so we can put parentheses here, right? It means the same thing because the x minus 3 is the exponent. So we're subtracting from the x. So remember, when we add or subtract from the x, we have to go the opposite direction. So subtracting from x means we're going to shift right 3 units. Okay? Remember, with the x, it's opposite. Okay? And you can see that from the graph here, right? They shifted the whole thing. This is the original graph here. They shifted everything to the right by 3 units. And you can see that 3 units right in here. Remember, the basic exponential crosses the y-axis at 0, 1. Well, notice we have that same point shifted 3 to the right. Okay? All right. A couple other examples here. Now, same thing, we're still comparing this to y equals 2 to the x power. So notice we have a subtraction. We're subtracting 3 from the x value again, which we just did that one. So that part right there means, again, we're going to shift right 3 units. This time we're adding 3 to the original function as well. So in other words, we're adding to the y values. So that part means up 3 units. Okay, make sure you know these, all right? And you can see from the graph how that occurred. All right. Now this one here. All right, so y equals 4 times 2 to the x power. So the original function is 2 to the x power, but now we're multiplying it by 4. So think about what's happening. We're taking the original, the f of x, the y value, and multiplying it by 4. So it's going to stretch all those y values by a factor of 4. In other words, it's going to stretch the graph up. Okay? And that's what they're asking. And again, you can see that right there. Okay? All right, and then we have exponential growth and decay models. So you've probably done these before in physics classes or chemistry classes with exponential growth and decay, biology classes as well. All right, so there's all the different properties. These are exponentials. So there's not much that you have to really know or have memorized. I should say you just should be comfortable with these. All right. This is more important here, examples. All right, so here's a sales decay. So it pays to advertise. And it is frequently true that weekly sales will drop rapidly for many products after an advertising campaign ends. This decline in sales is called sales decay. Suppose that the decay in the sales of a product is given by this function here in dollars, where X is the number of weeks after the end of the sales campaign. Use this function to answer the following. All right, so it says, what is the level of sales when the campaign ends? So we have to think about that. What does that mean to us? So we have this function they gave us, S equals 1,000 times 2 to the negative 0.5x power. So that negative 0.5x is in the exponent. But it says X is the number of weeks after the end of the sales campaign. Well, when it immediately ends, how many weeks has passed? 0 weeks, right? So we're going to plug in a 0 for X. So don't forget your equal signs here. So it'll be 2 to the negative 0.5 times 0. Well, that is 1,000 times 2 to the 0 power. And remember, anything to the 0 power, be careful, is 1, right? So this is 1,000 times 1, which of course is 1,000. And since it's a word problem, we need to make sure that we put the dollar signs on it, the units, right? Okay. All right, next one. What is the level of sales 1 week after the end of the campaign? Well, same thing, but now we're going to plug a 1 in for the X. Which means it's 1,000 times 2 to the negative 0.5 power. Now, be careful of PEMDAS here, of course, right? Remember, we work inside the parentheses first. So you're going to use a calculator to do 2 to the negative 0.5 power, then multiply by 1,000. That's important. Watch your PEMDAS. And once you plug that into a calculator, you'll see you should get $707.11. As long as I did my math correct. We'll see. Okay. All right, moving on. Part C, use a graph of the function to estimate the week in which sales equals 500. Well, there's the graph right there. You can see that they're giving the answer of X equals 2, but we're going to do this algebraically. Okay. So sales, remember the function they gave us up here, S equals, that's the sales, right? So in other words, we're going to replace S with 500. So it equals 1,000 times 2 to the negative 0.5x power. We need to solve for X. Okay? So what we're going to do is first we're going to divide by 1,000. Right? We want to isolate that X. 500 over 1,000 is a half. You could put 0.5 or 1/2, doesn't matter. Equals, 2 to the negative 0.5x power. Now, if you remember how to do these types of problems, since we have the variable in the exponent, we need to use logarithms or natural logarithms. Doesn't matter. Most people use natural logarithms, so I'm going to show you. So we're going to natural log both sides. Okay, and if you don't remember natural logarithms, don't worry. We're going to cover those at the end of the next section. All right, so the rules of exponents say rules of logarithms say we're allowed to take this exponent to the front as multiplication. So we're going to do that. We have natural log of 1/2 equals negative 0.5x times natural log of 2. Okay, again, we want to get x by itself. So we're going to divide, since we have only multiplication here, we're going to divide everything that we don't want. We don't want the negative 0.5. We don't want the natural log of 2. So negative 0.5 natural log of 2. So now x is by itself, right? The negative 0.5 is reduced. The natural logs of 2 reduced. All we have left is x equals, and we can put that negative sign on top or on the side either way. So it doesn't matter. Natural log of 1/2 over 0.5 natural log of 2. Now don't think that you can reduce the 1/2 and the 2 and don't think you can reduce the natural logs, you cannot do that. That's a function. So this is one piece and this is one piece. You cannot alter them. Okay? You can punch that into a calculator and you will actually see this comes out to be 2. All right? Which is what they said graphically. All right? So again, use the graph of the function to estimate the week in which sales equals 2, so it's week 2. There we go. Okay, part D, it says, according to this model, will sales ever fall to 0? So in other words, let's try to plug in a 0 for S and solve. Let's see what happens. 0 equals 1,000 times 2 to the negative 0.5x. There we go. Again, very similar to what we did before in part C. We're going to divide out the 1,000. Well, 0 divided by 1,000 is still 0. 2 to the negative 0.5x. Again, we're going to natural log both sides, but here's the problem. That does not exist. Natural log of 0 does not exist. Because if you remember, so a little review here, natural log of something, x, let's say, means log base e of x, which equals some function, y, right? Well, if we put a 0 in there, log base e of 0 equals y, and if you remember the conversion, which again I'll talk about in a little bit, just kind of refreshing your memory here, and I'll go in deeper in the next section. But we would rewrite this as e to the y power equals 0. Now, e is a positive number. There's no exponent you could ever take a positive number to equal 0. So that does not exist. So therefore, no, sales will never be equal to 0. Okay? All right. The number e, so we just kind of worked with e a little bit right here, but just to refresh your memory, the number e is an irrational number, right? Irrational, remember, means you cannot write it as a fraction, with a decimal approximation of 2.718, etc., right? 2.71 is about where most people remember. The number e is used a lot in exponential growth and decay. All right, an example would be growth of an investment. So here's an example. If $10,000 is invested for 15 years at 12% compounded continuously, what is the future value of the investment? All right, so we're going to use this equation here, S equals P times e to the RT power. And here's what each of those variables means. So you should know these, right? You should know this equation. You should know what the 4 variables means. S is the final amount in the account. Principal, which means the amount you put in. Interest rate in decimal for R, and T is time in years. Okay? So we're going to plug and chug, right? So the final amount equals the principal. So they put $10,000 in. Times E, remember E is a number, and you'll be able to punch that into your calculator, raised to the R, so 12% in decimals, 0.12, T in years, 15. So if you punch this into your calculator, now of course make sure you do PEMDAS, so I would do the 0.12 times 15, then take E to that power, then multiply by 10,000, and if I did my calculation correct, you should get $60,496.47. Okay, so try that problem out. All right. Next section. Logarithmic functions and properties of logarithms. So this is what I was talking about before. We're going to talk about those logarithms again. Let's see. So logarithmic function. So there's all kinds of fancy talk here. For x greater than 0, b greater than 0, and b not equal to 1, The logarithmic function with base b is this. So this is how we say this. Log base b of x equals y. Okay, so let's do that again. Log base b of x equals y. That's important that you know how to say that, which is defined by x equals b to the y power. Okay, let me show you how they did that. Now this is an important thing to know, is the conversion between these two. So this is, oops, spelling it wrong, logarithmic. This is exponential. Okay, so be able to convert between the two. So notice what happens here. If we take the b, raise it to the y, it equals x, right? So b to the y equals x. So I call that the little loop around, but that's not the official mathematical term. But that's how you convert from logarithmic to exponential. Okay, that's an important conversion to be able to do. Speaking of which, well, let's do some converting. Okay, so this is going back the other way, right? So we've got to look at that form up there. Look where the x, the b, and the y are. Okay? So we write it out. So we write log. So we're taking this exponential and turning it into logarithm. Okay, so it's going to be log base 4 of 16, and that's going to be equal to 2. And we check it. Check it with the loop around, right? 4 to the second power equals 16. That's what they gave us here. Okay? All right, so let's keep trying a few more of these. So b is 7 to the negative 1 power equals 1/7. So we write it like this. Log a base 7 of 1/7 equals negative 1. And again, we check it. 7 to the negative 1 power equals 1/7. There we go. Okay? All right, and one more using some variables. So this one will be log base 5 of x equals y. Same thing we did before, right? 5 to the y power equals x. There we go. Okay. All right, now let's convert in the other direction. So log base 8 of 1 equals 0. So this direction's easier to do, from logarithmic to exponential, right? Just do the loop around. 8 to the 0 equals 1. Again, remember, an exponent of 0 equals 1. Okay? That's important. A lot of people forget and for some reason put 0. Okay, moving on. So let's do a little graph. So we're going to graph y equals log base 5 of x. Okay? All right. So what we're going to do here is we're going to have these values plugged in for x, and we're going to figure out what the y is. So here's an easier way to do this. So watch. So we have y equals log base 5 of x, right? Well, we're going to use an x of 1 over 25. So y equals log base 5 of 1 over 25. So let's do the loop around. Right? So this means 5 to some power equals 1 over 25. Okay? So there's a way we can solve this, and that is, since this left side has a base of 5, so 5 to the y power, we want to convert the right side to be 5 to some power, and then therefore y will equal that number. Watch this. So 1 over 25. I think we can all agree we can rewrite that as 25 to the negative 1 power, correct? Negative 1 power means flip the fraction. Okay, but we want a base of 5, right? Well, 25 can be written as 5 squared, right? So this is, so 5 to the y equals 5 squared to the negative 1 power. Now your rules of exponents say exponent inside the parentheses, exponent outside the parentheses, we multiply the exponents. So 5 to the y equals 5 to the negative 2. Now there's a rule in math when we have the same base here, the exponents must be equal to each other. Okay, in other words, y equals negative 2. Okay, and you can do that same process for x equals 1/5. Right, you'll see the answer is going to be negative 1. And again, repeat the process for x equals 1. That'll be 0. And again, repeat the process for x equals 5. That'll be positive 1. Okay, so then we plot these points. So let's see, we have, and you're going to approximate, of course, 1 over 25 as an x value is really close somewhere here, right? So that'll be negative 2. X equals 1/5 will be a negative 1, so it's a little further up here. I know these may not be accurate, but they're approximations. And then 1, 0, and 5, 1. Okay? And draw this in as best you can. I know it's not going to be perfect, but there we go. Okay? All right, and properties of logarithms, read over these. Again, you don't need to memorize them, but you should be familiar with them. There's some graphs of logarithms. All right, so next example here, explain how the graph of each of the following functions compares with the graph of y equals log x. Find the domain and graph each function. Okay, so we're not going to graph these. We're going to skip that. I would cover that if we were in class, but it's a little more difficult to do that here. So let's look at these. Part A. Notice what's happening. We're adding to the x. So remember, when we add or subtract to the x, we go the opposite direction. So adding would mean we move left 3 units. Okay? All right, part B. Now we're subtracting 2 from the x, so that means move right 2 units. Okay, so we're moving the original graph, the logarithm graph. Right 2 units, but then the plus 4 means up 4 units. Okay? So make sure you're comfortable with shifting graphs. All right. Next, this is a very, very important section here. Logarithms, natural logarithms especially. So properties of logarithms. So the logarithmic function with base e is y equals log base e of x, defined by x equals e to the y for all positive numbers x, and denoted by, so this is the notation, we used this a little bit ago, but ln, we don't say ln, we say natural log. I know it's kind of weird because natural log would be NL, but this is ln. I believe it's a Latin thing, if I'm not mistaken. But either way, natural log of x, don't say ln of x, it's natural log of x, is the same as log base e of x. Okay, it's just like a shortcut. Okay, properties of log, so that one's important, know that one. And these you should memorize, all these properties. Okay, you should have them memorized. All right, so for b greater than 0 and b not equal to 1, the first property here that you need to know is log base b of b equals 1. And you may think, well, why is that? Well, let's test it with the loop around, right? We would go like this, right? So we would say b to the 1 power equals b, right? Well, yeah, that makes sense. Anything to the 1 power is itself. Okay, so log base b of b equals 1. In other words, whenever the base and the argument here, so that big B is called the argument, whenever those are the same value, the answer is 1. All right, property number 2, log base b of 1 equals 0. So again, let's test that with the loop around here. B to the 0 equals 1. Yes, that makes sense, right? Anything to the 0 power equals 1. So whenever you see a 1 in the argument, doesn't matter what the base is, the answer is 0. Okay, next property, log base b of b to the x power just equals plain old x. And that's because we're allowed to take exponents to the front as multiplication and then we would use rule 1 to see it would be x times 1. Okay, this property 4 is not used very often, but it's handy when it comes in, when it works, or when it's given. So b, and then this is all the exponent right here. B to the power of log base b of x equals x as well. Number 5, for positive real numbers m and n, if m equals n, then log base b of m equals log base b of n. In other words, it's an algebraic step. It means you're allowed to take the logarithm of both sides of an equation. It's going to help you solve problems. Okay, these are very important as well. The other 5 are as well, but you need to know these. So we have the addition, subtraction, and exponent rules for logarithms. So log base b of m times n, in other words, when we have multiplication in the argument here, we're allowed to break this into 2 logarithms with addition. Okay, see how that works? Very similar for division, we're allowed to break the division into subtraction of 2 logarithms. Okay, and the order is important here, so make sure you know the top one always comes first, the bottom one always comes second, always. That's important. And number 8, I kind of touched on that a little bit, and number 4 up there. When you have an exponent here, you're allowed to bring it to the front as multiplication. Okay? All right. And vice versa, of course. You can bring this number up here as an exponent. Okay, so make sure you learn those rules. Then you can do the homework problems, because there's going to be a lot of problems with these. All right, so, look at the directions here. We write each of the following as a single logarithm. Okay, this one's multiple logarithms, 2 of them, right? So we want to write it as a single logarithm. So we're going to use the rule up above. Notice we have the same base, right? They're both base 5. With addition means we can convert it to multiplication. So this will be equal to log base 5 of x times y. Okay, so we used rule number 6 up there. All right, part B. So notice we have numbers out in front that are multiplication, right? Okay, we're allowed to take those up here as exponents. Okay, so we're going to rewrite this. Don't forget your equal sign. Log of a to the 1/2 power minus log of b to the 5th power. Now, if you remember, 1/2 power can be rewritten. It doesn't have to be, but it can be rewritten as the square root of a. So I can't write. There we go. Minus log of b to the 5th. Now we have this subtraction here, so we're allowed to do this. Make it a single logarithm. First one, radical a over second one, b to the 5th. All right, and there you go. Now you have a single logarithm. So in this one we used rules 8 and 7. Okay. All right, one more. So we have natural log of 7x minus 2 natural log of z. So rule 8 says we're allowed to take that as an exponent, so don't forget your equal sign. So natural log of 7x minus natural log of z squared. Now we have a subtraction here, so we're allowed to do division. First one divided by second one. So natural log 7x over z squared. And now it's a single logarithm. Okay, practice those. Logarithm rules are extremely important for pre-calc, calculus, and beyond. Okay, make sure you know those logarithm rules. All right, thank you.